research center. He's a very experienced industrial, or experienced researcher in an industrial setting, which is a little different than what we often have at our workshops. So we really value him coming. He's going to speak about nanosensors for aerospace and building industries.
Afternoon. Between you and the break, I'll be brief, I promise. So my name is Sameh Dardona. I'm a principal research engineer at UTRC. I will start this talk by talking about DTC in general, what DTC is about and what we do in terms of business and products. And I will also provide some description of our initiative in the area of advanced manufacturing, including sensors and some other electronic components using direct write and electronics printing technologies. And then I will end up with some application examples as well as highlight some contracts we have with NextFlex Institute. I will also describe that institute as well and what we do with it as a member. So United Technologies is a large company that has 4 business units, right? More or less like GE Corporation. So we have business in the area of aerospace and building management technologies, and the 4 units that kind of create products for us are Otis Elevators. This is a company that makes elevators and escalator systems. We have a second one in the aerospace industry called Pratt & Whitney, and they're making aircraft engines mainly. And then we also have a business unit in we call it the CCS, or the Controlled Climate and System or Security Systems. This is a business that combines many small companies dealing with systems and subsystems for building management, including HVAC, security and intrusion and access control technologies. And the 4th one is aerospace systems. This is a new one that combined legacy Goodrich and Hamilton Strand together, merged 3 years ago. And they provide a lot of components for Airbus and Boeing, including landing gears and climate control for the cabin, interior designs, and some of the sensors for altitude and for other functionalities. They also provide de-icing and ice detection systems and technologies. So the research center for UTC is kind of a global entity right now. We have offices in the US, we have ones in Europe, we have also one in China, as well as well, the ones in Europe are basically in Italy and Ireland. So the main campus is in East Harvard, Connecticut. This is where most of our facilities and staff exist. So so what we do, we work with our business units. We work on technologies for the future. We look ahead. We look in what will change our products in terms of improvement, and we also look into ways of making things better for our business units, coming up with innovative solutions and ideas that can be added to the products to provide competing edge. So the areas of activities for the research center include advanced manufacturing, things like aerodynamics and acoustics. We do have a lot of material development and measurement activities. We also do have activities in the area of power electronics and circuit designs, as well as communications and thermal management. And those are all supporting the aerospace and building technologies. So we collaborate. We actively work with universities. We work with government agencies. We work with small companies, and we also work with competing industries as well to form partnerships. We write joint proposals and so on. So there's a lot of activities that we do in the US and outside the US to create sort of growth and progress for our industry. So the Advanced Manufacturing Initiative at UTRC was launched 5 years ago, and the idea there was to kind of map what we can do in the area of direct write and print electronics for the corporate at large, right? So this is an activity that sort of looked into what is there in terms of direct write and fabrication and manufacturing of sensors and active components, and where those could be utilized within UTC products, right? So on the top, you can see that, I mean, in the aerospace and building industries, there's a lot of need for sensors and actuators and functional devices, and those include things like de-icing, detection of ice, detection of pressure, detection of strain, temperature. I mean, in the building management, we look into smoke detection, fire detection, flame detection. We look into access control. How do we control the access on buildings? How we measure if there is an intrusion event and so on. How we counting people sometimes, even tracking people movement in buildings to control the ventilation and control the energy of buildings and so on. A lot of needed sensors that we kind of use right now and look for even using in the future. In terms of direct write technologies, we have been looking at all options for printing and manufacturing sensors, right? So this is a list of things that you can use to print and integrate functional coatings or devices into flexible or rigid substrates, or even make them into your product surface right away, so embedding them into the surface of the component. So we have been looking at things like screen printing, aerosol jet printing, extrusion printing, inkjet printing, thermal spray, and so on. We have most of those components, and the ones we don't have, we work with outside vendors. We collaborate with other companies, small companies, and other universities to sort of prototype and develop concepts in this area. So I will go through the description of two key technologies we have at the research center, and those technologies are meant to enable us to kind of manufacture, design and manufacture sensors and other electronic circuits in our products. So the goal here is really to look into what is available there that we can use to integrate functional sensors into our components. And one example is the aerosol jet printing machine made by Optimic. So this is a technology that uses kind of nano-dispersed materials. So this is relying on mainly nano or micro-dispersed inks, and then usually you have your ink suspended in a solvent, and then you use atomizers using ultrasonic or pneumatic methods to atomize your nano ink, and then create a mist, which is really small spheres, microspheres of particles that are aerosolized or carried through tubing with a gas flow. And then this is being fed into a small nozzle at a controlled rate, and then at the nozzle exit, there is a sheath gas that kind of forces the aerosolized particles into the substrate. So you control the atomizer, you control the flow rate, and you also control the pressure or the flow rate of this sheath gas, and eventually you will be able to control the trace, how much you deliver in terms of ink or nano ink, and you control eventually the geometry of your trace, thickness and width, right? You also can have options of replacing this nozzle using different sizes and so on to come up with some variation of trace size, right? So this is a very, very robust machine if you can get it to work. It needs a lot of tweaking and kind of alignment to really get this to operate for long hours. But once you get to work, you go through the steps of making all the needed tweaks and tuning, then this can print really consistently and fancy and good designs if you wish. So this video here is kind of showing it's going to work, right? So this video shows basically the printing of resistors using carbon nano inks, right? So this is the good thing about this one is also the standoff distance. So when you print, you are not touching the substrate. You are like 5 millimeters out from the substrate surface. So that means if your substrate has roughness or has other features in it, you are away from that, and you will kind of spray on it and away from it, which is really helpful for some designs and for some substrates, right? this is printing resistors on a substrate. And then the second technology that we rely on in prototyping and creating some of the designs we need for our application is made by Inscript. This is micro dispensing technology. This relies on kind of a syringe pump, really kind of simple. You load your ink to this syringe here and you apply a back pressure to it. So you keep kind of a back pressure at the ink, and your ink can really range from low viscosity to high viscosity. It could have nanoparticles or even microparticles. It's kind of very broad and flexible in the material type and characteristics. And then you control the opening on at the end of the syringe by having this valve moving up and down with high precision. Therefore, you can really control the amount of ink you feed into the nozzle down to 10 picoliters, which is really very tiny. Good control on the amount of ink. And then you have a conical nozzle at the end made out of ceramics, very robust and reliable. And you can feed through that with this process. This machine has pick and place. It has more than one deposition head. You can have 2 of them or 3 of them, which means you can print more than one material. You can mix and print different materials in the same design. And then it has also 3D surface mapping, which means if your surface is a non-planar, if it's curved or it's like a sphere or cylinder, you can map it, scan it, and then you can print on it. So this video here shows the printing of an active circuit. You can see that you have one printing head that prints silver inks, nano inks. And then you can also have another printing head to print the conductive adhesive, right? So this is a separate print head that comes and prints. I think it should continue, right? Hopefully. Prints the pads from using conductive ink. And then you have a pick and place arm built into the same machine to pick ICs, thinned ICs, and place them where you need them. So this is an example of being able to manufacture a functional device with the same machine, feeding one design into the machine. So your design, in this case, is a CAD file that integrates basically all those elements and specifies what material to use and when to pick and place and what to pick and place from the tray. And then eventually you have one functional device with just one design and more than one material. So I'm going to go through a few examples, application examples for some of our business units, and I'm going to describe them and highlight how printing can help us and how nanomaterials is being effective in those devices, right? So the first one is really sensing the wear or the degradation of a coating. So we do have a lot of mechanical surfaces or moving components, I would say, and those components they usually have kind of a coating on them for some reason. It could be meant for encapsulation. It could be meant for thermal kind of protection and so on. And we'd like to track any wear or damage to those coatings usually. So, and this helps us kind of understand when to worry about maintenance and when to kind of stop using the parts and go into repair and so on. So this example shows you basically an embedded design where you really can have your coating and then you design your sensor. And in this case, it's very simple design, right? It's really just think about resistors being in parallel configuration, and you have lines that are kind of located where the wear events would happen. And those lines are discrete lines, obviously. And then the idea here is that when wear happens, it's going to remove the lines one by one. Those are really thin and narrow lines, right, in your coating, extended in the coating thickness. And then if wear happens, then you are removing the lines. And when the lines are removed, you change the resistance of your circuit eventually. So for this concept, you need to do a little bit of circuit analysis and a little bit of simulation. So if you have, as you know, if you have many resistors in parallel, if you take one of them out of the circuit, then the change is 1 over n. Very tiny change, especially if you have large number of them, right? So to make this design kind of effective and work for a small number of resistors, right? Then you need to customize your circuit such that you don't have the same resistors. You have different resistors, but you have the same delta V or delta R every time you lose one resistor, right? So you'd go with this kind of approach. And then this is kind of showing a prototype to show how this concept could be fabricated with nanomaterials, right, and nano inks, right? So this is fully printed weird sensor that's made by the Inscript machine that I just showed you before. So this is showing that you can print those silver lines and you can make them really close to each other. So obviously the resolution of the sensor, the resolution will depend on the line spacing here, right? The more lines you fit per unit per millimeter, the higher resolution of the track of the wear event and the damage event and so on. So showing that you have many lines next to each other. And then you can also print those resistors as well. So you have the ink that really prints the right resistor. And the advantage here is that if you take this design and you look for resistors that are commercial, kind of surface mount resistors that are commercial, you will not be able to find the exact number. You have to sort of trade off some of the values, because in the design, for example, a resistor could be 131 ohm. And if you go out to the catalog to look for this value, it doesn't exist. Nobody will have this in the inventory, right? But with this technology, if your design says this resistor should be 211 ohm, you can print that number with this technology using nanomaterials and using the printing technology that we have. So this is one area where printing resistors and passive components really could make it more like an analog kind of process, right? And then testing this device, you can see that this is experimental data where if you remove the lines, you can get really even change in voltage as a function of depth or as a function of wear or time in this case, right? So a second application example for nanosensors and nanomaterials is kind of flame detector or flame sensors. This is an area of interest for us because we, as I mentioned in the beginning, in the morning session, we do have a lot of kind of need for smoke alarm, and if we can combine smoke detection with flame detection, then we'll have kind of better safety measure of the space, and especially in buildings where there are children and kids. Sometimes they play with flame and fire, and if you can report to that early on, we'll avoid accidents and bad things, right? So this is a design that shows photoconductive methods where you print electrodes that are interdigitated, and this is also printed using silver nano inks, and then on top of that you print an active photoconductive layer, right? So in this case, this is zinc stenate material, and the good thing about this kind of material is that you can tune the band gap or the absorption wavelength by tuning the size of the particles. So this is a nano formulation that we also worked with the university to create for this prototype, where this class of materials has a wide band gap, right? And then you can tune it, make it even wider by changing the size and the doping level of the nanoparticles. And the reason we need to do that, because we're trying to be solar blind. We are trying to move the detection zone more into the short UV, and that means we are not going to be responsive to any solar radiation in this technology. So this is an area where we still need some improvement, but just showing an example of where nanomaterials could sort of improve the quality of those devices. So a third application example is in the area of smoke detection, and what you see here is more like a concept for creating electron beams, right? This is probably new, but what the idea here is that you are going to rely on nanoneedles or CNTs to work as a cold cathode, and usually they are packaged in vacuum, and then you are expecting to create field emission effect if you apply a small voltage across the CNTs, right? So this is kind of a field emission device, and you emit electrons in vacuum. So if you can design what we call electron window, where your window is made out of supporting structure with open areas or open kind of zones, And then on top of that, you have a very thin layer of boron nitride or light kind of atomic weight material. You will get to the scenario where those electrons will go through the opening of the structure and through the membrane and travel into the outside. So this is more like creating environmental friendly electron beam source, right? And the way this could be used in smoke detection is that those electrons will eventually ionize the air outside the window and create a baseline of current. So if I measure the current that those electrons will create, I'll have a baseline of how much current there is. And if those emitters are stable over time and they create the same amount of field emission, then this current will be the same, roughly. But this current will change if there's smoke. If you have smoke particles coming this way, what will happen is that they will interact with those electrons and reduce the amount of ionized air. And therefore, you will know that there is a smoke or there are particles in the vicinity or in that space, right? This is the principle or the mechanism of sensing smoke and particles or even gases. And then one remaining challenge for this technology to be deployed is really the lifetime of those cold emitters. So we have been doing a lot of testing and evaluation and looking for materials that are pretty stable and consistent in creating those field emission characteristics for a long time. Because again, the lifetime for those devices is very long, and we need those to be qualified for this kind of performance. So this slide is describing the next Flix Institute. This is again more like a public-private consortium of companies, universities, and non-profit organizations. And the mission here, or the idea, is to improve or mature the flexible hybrid electronics technology in general by addressing some of the remaining gaps to enable manufacturing flexible hybrid printed platforms for biomedical, aerospace, automotive, and many industries, right? And flexible hybrid here means the idea is not to print everything. The idea is to print what can work when printed and then pick and place thinned ICs. So for example, right now, nobody can come around and claim that they can print a microprocessor or microcontroller, right? Or a memory, right? Those are the thinned IC that are being picked and placed into the circuit. However, you can print resistors, you can print capacitors, you can print interconnects and so on. And those will be printed eventually. So this is the meaning of hybrid here, right? So this is a list of member companies and universities, and UTRC is a member of that institute. They have proposal calls, and they have an open one right now. I think was released in May for those who have interest in this institute. So we are working with them on two activities, on two projects, and one of them is really looking into manufacturing high density sensor layer, right? So this is meant for improving the knowledge of aerospace components, right? We're trying to learn more about what happened to our components in the field during operation and trying to switch from scheduled to on-demand maintenance, right? So the way right now we operate is that we have this kind of scheduled maintenance, which means the engine will be taken into a repair hall after, for example, 2 years or 20,000 hours of operation, regardless of what the health is of each component of it, right? But that's a very expensive step to stop an airplane and take the engine out and inspect every component on it, right? So this technology is really meant to support us to move into condition-based maintenance, which means we are going to have a pre-knowledge of the component health, right? We'll understand the strain, the load, the temperature, the cycles, and so on, before we decide whether we need to maintain it or not. And hopefully this is going to be cost effective and will save us a lot in the maintenance side, right? And this network of sensors will include temperatures, include strain and pressure sensing nodes deployed on a very small stretchable substrate. And eventually you can take the substrate and stretch it to the large size, and you can wrap it around a component, or you can embed it inside the component as a layer within the composite, and hopefully connect wires to it and understand the exact conditions and the health of that component, right? The second program with NextFlix is also, this one is led by UMass Amherst, and we are kind of a subcontractor on it. And the goal here is to demonstrate the manufacturing of wearable human performance monitoring platform. This is meant to be kind of wearable, which means it will be designed and made on a very flexible substrate. It's going to measure temperature, heartbeat, and oxygen level during and report on those wirelessly. And then the idea here is that many of the interconnects will be printed, many of the power management circuits will be printed, and additionally some high-end ICs will be kind of picked and placed. Therefore, there's going to be a lot of activity around die integration, die attachment. There will be a lot of activity on printing fine, narrow conductive lines using nano inks and so on. So this is led by UMass Emirates, and we and other small companies are part of this team. And I will end with this slide, and thank you for your time and attention. Yeah.
Have you ever tried to use the Sauropod with a company like Aerospace Dispensing sometimes now? I get mixed reviews with that, so I just wondered if you had any experience with it.
We have one. We used one of them, and the Sauropod is, I would say, effective in making kind of simple prototypes. And our experience is that because it's kind of capillary based printing, it's required that the printing tip is touching the surface to draw the ink at, verticals, which means that limits the kind of substrate you can work with, because you need to have eventually very smooth and flat substrate. So if you have rough or some porosity in your substrate, then this could create inconsistency in the printing profiles. And I would say it doesn't have a lot of added on features to enable mapping of surfaces yet. I think they are still improving on their design and their capability. Yeah, it's kind of, I would say, low-end prototyping tool as compared to the Optimic or the Inscript. Those are, I would say, those are high-end fabrication and prototyping die-try tools.
Any other questions?
Yeah.
I was wondering why you're using ruthenium particles.
Ruthenium.
Using ruthenium particles, you said.
Yeah. So this ink is made by a company called ESL, if you know it or not. So the reason we use this ruthenium is really the stability at the temperature of the application.
It's very expensive.
It is actually.
Yeah.
So the history for this sensor is that we tried carbon.
Okay.
And we tried other things, and they did degrade at certain temperature.
Mm-hmm.
This resistor material has been qualified for the temperature of interest for us.
Okay.
And has been very stable, and we have not seen any change in resistance as a function of temperature, I would say, or a small change compared to other materials. So, and it's a commercial one as well, so
Yeah.
very well, I would say, doubled by that company.
Okay. Thank you.